We continue on. I was just trying to remind you guys about your chemistry, that in your chemistry, you remember the aspect of mass, all right, and molecular mass. So if you have been given, for example, that a gas containing 2 kg or 2 grams or any amount of mass of any gas, you are able to, you'll be able to compute its atomic number. Why do you need to compute the atomic number given the mass? Why do you need to compute the molecular mass given the mass? Is you want to find the number of moles, all right? So you know that the number of moles, N, I'm sure you know that N, I'm writing it in this corner, N is equals to the mass given over the molecular mass, all right? So you can be able to find, if they give you directly to say, no, you have 2 moles of oxygen, then you can use it directly. But if they want you to calculate and then they give you, for example, the mass of oxygen or any gas, you can be able to find it, the number of moles that are contained, and then you can be able to compute your M over M, this mass given over the molecular mass, and then you'll be able to find this small n, all right? So remember, it's all coming from, we are trying to find out the proportionality between, we know that pressure and volume is equals to a certain constant, all right? Certain constant multiplied by temperature. So we want to find out this constant, all right? To find out this constant is where now this constant, we are saying this constant is given by this constant. This constant is very hard to write using your mouse. So this constant is what we are saying is given by M over small m over big M. Now, this small m over big M gives us the number of moles, but that's not the only variable or the only aspect we need to consider. We also need to consider there's also something called the gas constant, R. All right. So now this becomes something like, because small m over big M gives us the number of moles, all right, multiplied by R. All right, because the R is the gas constant. So this is what we get here. We know that volume and pressure is related to temperature by NR. All right. Now the value of R you will always be given, or you can even swatira it if it's okay. So the value of R, which is called the gas constant, all right, it will be given as this number. All right. If they give you the ideal gas, the value of R in terms of 8314, have you seen there's this K here standing for kilo? This is when you are multiplying or doing your equations in terms of kilomoles. Here you have kilomoles. This other K is standing in for Kelvin. Kelvin is for your temperature. This K, the first one, is for kilo. So you have your 8314 if it is your kilomoles. But if you are just dealing with moles, have you seen there's no K here? Meaning your value will be, the point will be here. So it means you have divided this number by 1000. If you divide this number by 1000, you remove the K. What are you going to have? You're just going to have your 8.314. So that will be your R. All right, the value of R. So this is just to establish our concept so that when we start looking at examples, you'll be able to know. Like I'm telling you, again, I will emphasize, we are not going to talk about the mole concept because you did it in chemistry. It will be a waste of time, but it can come. It comes actually in your quizzes, in your exams and whatnot. It can come. So what I would advise you, if you've forgotten about your more concept, go back to your chemistry, or you can read the notes that were sent to you on thermophysics, on this chapter that we're looking at. Then you can just refresh your memory on the more concept, because you would need it. All right, is that okay?
Yes, sir.
Yes.
Yes.
Awesome, awesome. So we continue on, and then when we continue on, like I'm saying, the final expression which puts into consideration the pressure, the volume, and the temperature is given by pressure, volume, and R times temperature. And this is what is called the ideal gas law. Ideal gas law. So now if we have an ideal gas law, it means that any gas that obeys the ideal gas law is called an ideal gas. Ideal gas. It obeys the ideal gas law. And most of you guys don't like obeying laws. Parents say you should be offline at 22 hours, but do we obey? So are you an ideal gas person? We'll find out.
Yes.
Okay. So we are going to find out by doing what? Finding some examples, solving some examples. Now these examples, I got them from your notes, and yeah, so I'm going to try and explain how they came up with the answers and what's going on. So we'll have someone to read for us the first question that we have. Let us have Eunice to read to us the first question, example 10.2, the one which has been written, example 10.2.
Okay. Find the volume that 1 kilomole of an ideal gas occupies under standard temperature and pressure.
Awesome, awesome. So it's a very nice question because it deals with so many concepts. Have you heard of this? How many of us have ever heard of standard temperature and pressure? Sorry, standard temperature and pressure. How many of us have ever heard of that terminology?
I've heard it before.
Awesome, awesome. So, yeah, we are going to explore just a bit to find out what they mean by standard temperature and pressure. Okay, maybe Sante, you can even go ahead and tell us what is meant by standard temperature and pressure. What do you think is meant by standard temperature and pressure?
I can't really explain it well, but this is the temperature, or this is the standard scientists use to measure temperature, whatever. It's estimated to be about 22, is it 22.4? Somewhere there. So that's what they use, scientists. That's what I think.
Okay, okay. Now, anyway, the idea, I'm sure the idea is there, but standard temperature and pressure. So standard, what is the standard temperature? The standard temperature is 0 degrees Celsius, all right? So 0 degrees Celsius, that's the standard temperature. And what is the standard pressure? Standard pressure is 1 atmosphere, all right? So standard pressure is 1 atmosphere. So you know that the atmosphere exerts some pressure on us. So this is a standard. The standard temperature is 0 degrees. So just referencing to the ice melting. And then the standard pressure is 1 atmosphere. So you expect that if they give you a question and then they talk about standard temperature, you know that your temperature, on the part of temperature, you should be talking about 0 degrees. So that is your standard temperature, and your standard pressure is 1 atmosphere. All right. 1 atmosphere. Now, 1 atmosphere is equals to 1.0325 times 10 to the power 5 Pascal. This is if you were to convert it into Pascal. If you want, if you are like me, I may not even convert it into Pascals. I will just say 1 atmosphere. I'll just say 1 ATM. Oh, sorry. Now let me just erase that. Yeah, let me just remove this. So otherwise, this is what is meant by standard temperature and pressure. All right, 0 degrees at this pressure code 1.01325 times 10 to the power 5 Pascals. It is called 1 atmosphere. And the temperature that is used at standard temperature is 0 degrees. And you know that, like I explained in the previous lecture, we say that temperature, whenever you're doing calculations in ideal gases and whatnot, in physics, whenever you're doing calculations, usually you convert your temperature to Kelvin. How do you convert your temperature? You get your temperature in degrees Celsius and add 273 to get your value in Kelvin. All right. But if they said room temperature and pressure, RTP, who knows the room temperature, the standard room temperature? Someone to help us? Room temperature? If they say standard room temperature and pressure, someone to help us?
20 degrees Celsius.
Okay. Sometimes you may go for 20. Sometimes you may go for 25. Sometimes you may go for 22. So it depends. It usually, sometimes they will give you these things. But I want you guys to go and research the actual one, which they use between 20, 22, and 25. All right, you'll find these values. So find out which one is the room temperature, standard room temperature. But the standard pressure is the same, 1 atmosphere. But if they say standard temperature is usually 0 degrees. So
Can it be 24?
Yeah, it might be 24, but I want you guys to research and get the actual value. All right, Google or whatever means you may do to get the actual standard temperature. Yeah, because it might come in your quiz, who knows. So this question is,
sir,
what
of the one which they would use in the notes actually on Mundo? Is it fine if we can just stick to that?
Yes, they use 20.
Yeah, if I may remember very well, I think it's 20.
Okay, good. But confirm. The other guys, you should confirm, because yeah, you need to have the correct stuff. So we continue on with our example. Remember, our example is saying, find the volume of one. Now imagine they have even used the word kilo. They have not just said 1 mole, so they have used kilo. If they have used kilo, I told you that the error that you have to use is 8314. All right. If they just used the word mole, then we're going to use error as 8.314. You'll be able to see in the equation. So we have 1 kilomole of gas at standard temperature. So we want to find its volume. What do? We use this formula. They've already given us the number of moles, this N. They've already done for us mass over the molecular mass. They've already given, if they give you the number of moles, then you know that your N value, N, is that, this N, this equation, all right? So this will give, for us to find the volume, we know that we know the pressure, we know the number of moles, 1 kilomole, and the error, this error value, this error term, we are using 8314. And this is just joules per kilomole. Don't worry about this. These are just units. Multiplied by, all right, the temperature. What was the temperature? The value of T. Value of T, we have found it as what? 0 plus 273 is what? It's the same as 273. Now, when we solve this equation, we are solving for what? For volume. What is the volume? So when we solve this expression here, when you solve this expression there, all right, we solve for V. I know you know your algebra, very easy. That's how come we get our volume being equal to 22.4, all right? So 22.4 is the volume that you would get. And volume is in what? What is the units for volume? It is meters cubed. Now, because we are talking about kilomole, you still specify meters cubed per kilomole. But if you are just talking about moles, if they didn't use this K, they just wrote moles like that, then you are going to use, at the end, the volume will be meters cubic per mole. You are going to use just the word mole. All right. Are you guys clear on how to go about this question? How we can use this question? How we can solve it?
Yes.
All right. So, like I said, if your mic is muted. Okay, Precious, you have a question? You can go ahead, Precious.
Yes, like on the R constant. Yeah, on the R constant. So you can use n of the two, the one which is in kilomole, information that you've been given in the question. The standard one, how is it?
Okay, so I said that here, in fact, I've even made a note here, down here. I've said that you use R, this R constant with kilomoles per kilomole like that. If you, for example, in this case, we have been given, say, find the volume of 1 kilomole. All right, they've even specified 1 kilomole. So we're already talking about kilomoles. That is why it is very, you can use the one that has kilomoles, the R constant, which has kilomoles. But if they just said mole, if they just said 1 mole, instead of saying 1 kilomole, then if they just, when we are dealing with kilomoles, we use this, the one that has kilo in it. But if we are just dealing with moles, we use the one that has 8.314. This is, we use it when we are just dealing with moles. Is that okay?
Okay, thank you.
Yeah, so that's how come we use the 8,314. Yeah. So any other question before we move to the next question?
I have a question.
Okay.
Okay, I don't know if it's just in the algebra, but how come when we're dealing with kilomoles, aren't we supposed to have a larger volume since we're looking at more particles?
Okay, so now have you seen, even here at the end we have used the word per kilomole. So if you want to have it per mole, what you do, you multiply this, you multiply on top by what? By 1,000. If you multiply on top by 1,000, what do you get? 1,000, remember, represents K. So your K will cancel on top and your K down will cancel. Then you have your final volume will be 2,240 meters cubed per mole. Right? It's hard for me to write using a mouse. So yeah, but you get the concept, right? Because down here we have still maintained the word kilomole. per kilomole. So the 1,000 has been cancelled out. Of course, we were supposed to have a larger volume, but we have maintained this word per kilomole.
Okay, makes sense.
Okay. So we go to the next question. Are we okay? Like I said, I think, Sante, you had a challenge with unmuting your mic and whatnot. When you have a question, you can unmute your mic and then you ask so that you can follow it. Are you able to hear me, Sante?
Yes, I can get you.
Okay, awesome. So we'll continue on if there's no other question. So in fact, Sante is going to read for us example 10.3, and then we can continue on that note.
I can't see clearly, but I'll try.
Because
An empty oil drum. Yeah. No, they're too small. An empty oil drum containing air is closed at temperature of 20 degrees Celsius. It is then set out in the sun where it heats up to 60 degrees Celsius. If the original pressure was 1.0 atmosphere, what is the final pressure in the drum?
Awesome. So you guys, you discover that there are quite some interesting facts that they have brought up. What is that? Is that an empty oil drum containing air is what? Closed. So if we have a drum like that, all right, if it's tightly closed, we expect its volume to be what? Fixed. So in our calculations, we'll not be talking about volume. Its volume is fixed. All right. So we have air drum is fixed, and the volume is fixed. They tell us the temperature of that drum is at 20 degrees, and they put it out in the sun. All right. So that its temperature rises to 60 degrees. But its original pressure was 1 atmosphere. So they have used the word 1 atmosphere. If they didn't want to use the 1 atmosphere, they would have used the value 1.013 and whatnot times 10 the power 5. The power 5 pascals. All right. So with pressure, don't worry about the units. With pressure, whatever units they give you, you can work with them. But with volume and with temperature, you always have to make sure that your units are incorrect. Volume in meters, temperature in Kelvin. But with pressure, you can use whatever units. So here, if they've given us pressure as 1 atmosphere, let's work with one atmosphere. So they're saying, what is the final pressure in the drum? So we know that temperature 1, we're at 273. And when we add the temperature in degrees Celsius, we get our 293. And temperature, in fact, this was supposed to be temperature 2. Yeah, subscript there. Temperature 2, 273 plus 60, we get our 333. We know our pressure 1. What is our pressure 2? All right, pressure 2. We don't know it. So let's find out. Are we all clear on the question so we can look at the solution?
Yes, sir.
Awesome.
Yes.
So I just also brought out this so that you guys can just get a glimpse of what is happening. So remember, the equation that we had even in the previous expression was, we said that P is equals, PV is equals to N R T. All right. This was the expression that we had. All right. Now, if we have pressure 1 and temperature 1, suppose the volume is constant, and then we have another pressure which we are looking for, pressure 2. The volume is still kept constant. This goes to N R T. Now, this other temperature is temperature 2. If we divide these two equations, All right, equation 1 and equation 2. We divide them out. What will happen? Volume and volume on top will cancel out. nRT and nRT will cancel out. So the expression that now we'll have is pressure 1 over pressure 2 is equals to temperature 1 over temperature 2. All right. This equation is what we had earlier on when we were dealing with the ideal gas laws and just trying to derive some of the expression. Is the expression that we had here. All right. This word was supposed to be P, pressure. All right. Pressure 1. Oh no, it is supposed to be temperature still. Well, yeah. So let's see if I can remember where I put the expression that we're supposed to look at. All right. All right. Anyway, but the expression that we have is here. All right. Such that pressure 1 over pressure 2 is equals to temperature 1 over temperature 2. This is the same as saying pressure. If we want, we can say pressure 1 over temperature 1. We can even put temperature down here is equals to pressure 2 over temperature 2. It's the same expression as that one of saying pressure 1 over pressure 2. If we want the ones, we can put them on the same side, meaning pressure and temperature, we put them on the same side, and then pressure and temperature on the other side. If we want, we can just, I'm sure you guys are able to see what is happening here. This expression, we have gotten it by dividing this equation and that equation, but you don't always have to be doing that whenever you are doing calculations. You can even master this equation here, and you know that pressure 1 over pressure 2 is equal to temperature 1 over temperature 2. You can still write it in this format of saying pressure 1 over temperature 1 is equal to pressure 2 over temperature 2. Are we okay on that note?
Yes, sir.
Okay, I take it that way. So we know that our pressure 1 was 1 atmosphere. Pressure 2, we don't know. Temperature 1, we had 293. Temperature 2, we had 333. So manipulating this, we get our pressure 2 as, 1.14 atmospheres. So the pressure increased to this point. All right. So today, in terms of examples, we'll end here. But actually, this is actually even where the topic ends. But for the sake of preparing for the quiz, I would prepare more questions. Hopefully, God willing, we can go through them on Thursday to make sure that you guys get to grasp the concept more. And I'll try to have some more questions talking about more concept, so that even as you revise to go back to look at your more concept, you'll be able to see the questions, how they go. Is that okay?
Yes, sir.
Yes.
Awesome. And as you know, the WASIS are custom. I always give you homework. So there's a homework. I'm going to send this document to you, and hope that you guys can do the homework in time. And yeah, if we don't have any other question, we can end our meeting here. Do you have any other question? Okay, seems we're okay. So have a good day to you all.
Good day to you too.
Awesome.